Okay, now, if you followed me through to this point, you can see how I generated the reaction that will undergo hydrolysis. And you note that it's because it generates a weak electrolyte. If it generates a strong, you toss it. It's not going to react. So the ice table is always set around the reaction that generates the weak electrolyte here. Now this has a equilibrium expression, products over reactants, just like we've been working with in the past. However, the anions, if you recall from the last chapter, the anion is generally referred to as a conjugate base. Okay, remember talking about that? And I said anions, negative polyions, are conjugate bases. Well, this would give you a Kb value expression, an equilibrium constant for a base. But because it comes out of this hydrolysis, we're going to make it a Kb prime. Now the thing is, you cannot look up a Kb prime for an anion, but you can calculate it from a simple formula. Ka, whatever the acid is, see we have an acid in here, times Kb, whatever the prime is, always gives you the Kw value, 10 to the minus 14. So when we want to calculate the Kb, we solve this for Kb, and I just put a prime up there because I'm working, it's not the weak bases that you would have in a table. And that would be Kw over the Ka that's generated in the hydrolysis reaction. And so in this case, it'd be 1 times 10 to the minus 14 over 1.8, and that'll be given, minus 5, and that gives you the equilibrium constant for that anion conjugate base ionization reaction. I get 5.6 times 10 to the minus 10. So there is your K value. Now, when you put in the products over reactants, don't put in water in this. So the expression that you will be basing the equilibrium row on would be the acetic acid formed in the hydrolysis times the hydroxide ion divided by the salt anion. You see, I got that expression out of this fourth row, fourth equation. So if you want to mark that, that's where those substitutions, and again, do not include the water. Now you'll substitute the values on that row into that expression and solve for the unknown. And notice it will give you hydroxide. And so this would be x squared, x times x, over the salt ion concentration, which is 0.10, and that's equal to the Kb prime, 5.6 times 10 to the minus 10. And so therefore you can solve that and multiply both sides by 0.1 square root, and you'll have the hydroxide concentration. Once you get there, you should be able to get the hydrogen and ultimately the pH, right? Okay, so continuing, we have x to equal the square root of 0.10 times 5.6 times 10 to the minus 10. Please let me know if I'm going too fast for you. Molar. And now this is in hydroxides, as we showed you up here. So that's minus 10 times 0.1 equals square root. And so that's 7.48 times 10 to the minus 6 molar in the hydroxide ions. Sure I didn't, there's fire somewhere. Okay, so the pOH now is minus log of that. .12, and the pH is 14 minus that. This is 8.87, like that. So in the beginning of this, I showed you the equivalence point for a weak acid, strong base titration would go through, and this one's 8.87. So it shows the strong base, weak acid, pH is greater than 7, or in the alkaline range. But in working the problems that you will have on this, you will be given a concentration of the acid, or you'll just straight away be given the salt and concentration. I'll work one in a minute for you. But you either you always work it to the salt and test each one, and the one that generates a weak electrolyte is the one you analyze with a ice table. Let me go through the weak base titration. Okay, this is a strong acid, weak base titration. So the first reaction again is the acid-base reaction. So we'll take HCl plus ammonium hydroxide to produce the salt. So the ammonium and chloride hook up plus the water. Now we want to test the salt, so we need to ionize it first. So NH4Cl goes to ammonium plus the chloride ions, like that. Then the ammonium reacts with the water. I'm going to put the chloride first because it's a no reaction. Like this. Okay. Now, the one we want to analyze would be the cation reacting with water. And since that's a cation, it's going to pull the OH over and make a weak base. And so we need a Kb value for this one. Turns out to be 1.8 times 10 to the minus 5 is the Kb value for that one. And you are generating an excess of hydronium ions in this case. And with that excess, you will be, the equivalence point will be in the acidic range. Okay, so we want to assign, we can use a 0.10 molar salt generated, and which will give you 0.10 molar in the ammonium ion, and then make our calculation from there. Okay, so this is the fourth reaction in that sequence I just outlined for you. So what you want to do is set up an ice table with the one that generates the weak electrolyte, and for memory, there's your Kb value for the weak base, and that'll be given. So So you got initial change in concentration, concentration at equilibrium, and that is 0.10. Disregard the water, and it starts 0 and 0. And this is minus x, disregard water, x plus x plus x, and it's 0.10 minus x, disregard water, x, x, and this, you drop the x, 0.10 molar. Okay, so everybody okay on the ice table? Okay, so you can run the acid-base reaction, write out your ionization for salt, and then you test for reactions with water to see who generates a weak electrolyte. And then use that one as the one you would put the ice table to. Now, since we're working with a cation, that will be a conjugate acid, and so we'll define the Ka value this time as a Ka prime. And we calculate it the same way as Kw over Kb to get the Ka prime. So Ka prime is Kw over Kb, as we have the Kb value for the base generated. And so that would be equal to 1 times 10 to the minus 14 over 1.8 times 10 to the minus 5. And then 5.6 times 10 to the minus 10. Now, your Ka prime is equal to products over the salt reaction. Okay, so you have the ammonium hydroxide that's formed from the acid-base reaction. It generates some hydronium ions, excess, divided by your ammonium ion concentration from the salt. And so that'll give you x squared over 0.10 to equal the 5.6 times 10 to the minus 10. So with that, you can calculate the hydronium ion concentration, because X is, in fact, the hydronium, and then you take the log of that, and you have the pH of that at that equivalence point. So X, which equals the hydronium ion generated because of hydrolysis, is equal to the square root of 0.10 times 0.6 times 10 to the minus 10. It'll come out in moles per liter. I see 7.48 times 10 to the minus 6 molar in H plus ions. And so all I do is take the pH was minus log of the hydrogen, and that's minus log and we have a 5.12 pH at the equivalence point. So a plot of this one generates the traditional curve, except the equivalence point is 5.12 for strong acid, weak base titration. Okay, here's a problem that comes to you given the salt, and you will not be given, say, you won't be given the acid-base combination. So you're starting really with reaction number 2 in the list that I've given you. That's sodium propionate. And so sodium PRO plus minus goes to the sodium ions and the propionate ions. Okay? And then you want to test the sodium ions with water, and then the propionate ion with water. And so this is theoretically give you a sodium hydroxide and a hydronium ion left over, and this one give you propionic acid with excess hydroxide left over. And I'm giving you the propionic acid Ka in the problem, so that, like I said, it would be a given. And of course, the sodium will not react or undergo hydrolysis, so we can exclude that one from our analysis. But propionic acid is a weak acid, so yes, this last reaction here is the one we want to apply to the equilibrium table, or the ice table. So we're given a 0.025 molar. We disregard that. Now the propionic acid and hydroxide are going to be delivered in equal amounts, so I'm just going to shorten this to just to show the equilibrium row, because I don't need to fill up my page with an ice table. So once you get comfortable with this, you'll just go straight to that equilibrium table, because all of the problems will be equal amounts. They're always 1-to-1 ionizations for these hydrolysis reactions. Always 1-to-1. So now, since that's an anion, we're looking for a Kb prime, which is Kw over the propionic acid K value. And that would be H pro OH minus over the propionate salt ions there. And that ultimately goes to x squared over 0.025 and equals to 1.3 times 10 to the minus 5. So when you solve for x in this one, you're solving for the hydroxide, and then from there you get POH and then pH. So this little setup like this shows how you can condense all the noise I've been making about hydrolysis and what have you, but all you have to do is solve for x, which gives you the hydroxide as shown here, and that's the square root of 0.025 times 1.3 times 10 to the minus 5 molar. So our hydroxide is 5.7 times 10 to the minus 4 molar in the hydroxide right here. So that gives me a POH, OH. I'll hit the log button on that one. I get 3.24. And with that, I can get the pH at the equivalence point, 14 minus 3.24, and condense this down to 10.8 or 10.76. 6, 7, 9, 10, 7, 8, 9, 10, yeah, 14. So we're at 7.6 POH that. Add them up and you get 14. So I've tried to show you how it can be condensed. This is the salt ionization. This is reaction 2. And I tested each one. Of course, we're not going to use the sodium. So once you get comfortable, you'll just look at it. And you know that if you react it with water, that's going to give you, so a lot of people will just leave that one out and just go straight to the propionate, the weak acid generated, and work your problem straight down from that. Go straight to the equilibrium row, Ka, Kb, whatever the problem is, and we'll see that pH of the salt solution, right there.